Ordinary linear regression has a quiet weakness. When your features are numerous or highly correlated with one another, the fit can go haywire. The model produces enormous, unstable coefficients that swing wildly with the tiniest change in the data, and it ends up memorizing the training set instead of learning the real pattern. Ridge regression is the gentle, elegant fix. It keeps everything you love about linear regression and adds one small term that quietly reigns in those runaway weights. It is the most common form of regularization there is, and once you understand it, ridge, lasso, and elastic net all fall into place. Let's dig in. So what exactly does that extra term by you? Here's the contrast side by side. Plain least squares chases the training data as closely as it possibly can. Give it correlated features, and it overfits, handing back huge coefficients that fight each other and lurch around every time the data shifts a little. The fit looks great on paper and generalizes terribly to anything new. Ridge deliberately shrinks the weights towards zero. It gives up a sliver of accuracy on the training set, a little bias, in exchange for a large drop in variance. And the payoff is a model that stays calm, stable, and far more reliable on data it has never seen before. The magic lives entirely in the objective that Ridge chooses to minimize. Walk through how it's built, one piece at a time. Start from the ordinary squared error loss, the exact same fitting goal linear regression already uses. On its own, this term wants only to hug the training points as tightly as possible, which is precisely how the overfitting sneaks in. Now, add a penalty term, lambda times the sum of the squared coefficients. This is the L2 penalty, the heart of Ridge. It charges the model a price for large weights. So a coefficient now has to genuinely earn its size by reducing error more than the penalty costs. Weights that only exist to chase noise simply aren't worth their price anymore. Then minimize the two terms together. The model balances fitting the data against keeping its weights small, and the strength lambda tunes that balance. Set it to 0, and you recover plain least squares. Turn it up, and the penalty presses harder, pulling the coefficients in ever more firmly. The effect is that every coefficient shrinks towards 0, but never lands exactly on it. Ridge even has a neat closed-form solution, so it stays computationally cheap, and lambda itself is chosen by cross-validation to find sweet spot. Boil it down, and 3 ideas define ridge regression. It adds an L2 penalty on coefficient size. The sum of the squared weights, scaled by lambda, gets bolted onto the loss, so large coefficients are actively discouraged rather than freely allowed. It shrinks the weights to cut variance. By trading a touch of bias for a big reduction in variance, Ridge stabilizes the solution, which is exactly why it's the go-to remedy when multicollinearity makes least squares blow up. Correlated predictors stop fighting each other and settle into a calm, sensible set of weights. It keeps every feature just tamed. Because the weights shrink but never reach 0, Ridge does not do feature selection. Every input stays in the model with reduced influence, and that is precisely where Lasso, with its L1 penalty, goes further. All right, let's lock in what matters. Ridge regression is linear regression plus an L2 penalty that discourages large coefficients, the gentlest and most common form of regularization. It minimizes squared error plus lambda times the sum of squared weights, shrinking every coefficient towards 0 to trade a little bias for far less variance. It is the go-to fix for multicollinearity. It has a cheap closed form, and lambda is tuned by cross-validation, though scaling your features first is essential. Because it never zeroes a weight, Ridge tames every feature but selects none, which is the door Lasso walks through. Want the rest of the regularization family made this clear? We cover all of it at standarity.com. Come join us.